Okay, H3 production, I've already described this in some detail, so I don't want to go through all of this or belabor it, but here's that production reaction. You take hydrogen, diatomic hydrogen ion and react it with a neutral, and you can end up with an H3 ion and a neutral as a consequence, and that has an isobaric interference with your deuterium. And remember, deuterium is really, really small abundance in nature, and so even a little bit of this H3 ion can confound your measurement. And it scales with the amount. So here's an example. You can sort of vary the peak height of your hydrogen standard gas and measure the ratio, and then apply that slope to another unknown, and then end up with that nice flat delta value as a consequence. So it's fairly straightforward. It's been done for years in dual inlet mass spectrometry. There's no secret here. It's not a new thing. But it is bigger for the continuous flow techniques. The production of the hydrogen 3 ion tends to be more efficient for whatever reason in the ion sources where there's helium flow as well. So it can be a fairly large tens of per mil kind of correction. So it's important to pay attention to it. It's often in the software as kind of a canned number. And I don't know, I never like to be told what to do. I don't know, do you have that sense? And so I like to know what that number is, and I want to know who generated it and why, and is it right for today and the samples I happen to be running. So if you're working with hydrogen in these continuous flow things, pay attention to that H3 correction and understand what number you're using and whether it should be updated. That is the sort of the factory version of how to make that correction. Alex Sessions and working with John Hayes as part of his dissertation work came up with an alternative method to do this, which is very elegant, but it hasn't been incorporated into the commercial products. But you can do this yourself. He's developed a set of standards where there's varying concentration of the individual, so some that are really highly abundant and some that are very low in abundance. There's a smaller one here. And what's important about the sample set is that the delta values of the hydrogen are not correlated with the height, with the amount, right? So there's no correlation there. And then you can numerically calculate your H3 factor by minimizing the measured versus the known delta values of each. And there's an algorithm that they developed for doing that. So. Okay, well, let's pull our heads up out of the details here and talk about some of the other kinds of techniques that have emerged in recent years. So I've shown you GC for carbon, I've shown you GC for nitrogen, and GC for hydrogen on organic compounds. What I haven't shown you is sulfur, and that in recent years has been made possible by taking and literally a GC and wheeling it up and sticking the end of it into a Neptune ICP, inductively coupled plasma ion source mass spectrometer, and running it in, and then the sulfur is measured for individual peaks coming off of that. This is Amrani's work back, it was published in 2009. It's beginning to take hold in natural sort of environmental applications, but it's really taken off in the petroleum field. And it turns out that sulfur-bearing organic compounds carry a lot of information about maturity and process in petroleum generation, and they're also important because sulfur in petroleum is a hazard, and it's also a nuisance because it can corrode pipes and things like that. So it's actually become very kind of of great interest in the petroleum realm. Okay, so that's an example of kind of this expanding toolbox of compound-specific work. Some work that we have done and then has been picked up and continued by some others is the idea that you can pyrolyze a molecule as it comes out of your GC and kind of break it. It's not a full-on pyrolysis to H2, but it's sort of a gentle pyrolysis. And what we did is just decarboxylated an acid, an organic acid. So the carboxyl head group comes off as CO2, and then the rest of the molecule sort of sits down. And you can measure the CO2 as it comes off of that. So we published this some years ago now, and it's a Palladium reactor with a little trickle of hydrogen. And again, you don't want to blow anything up, but just a little bit of hydrogen, and you kind of let that until you get that nice stable CO2 production, And here's the reaction in a simplified form. We have some kind of organic acid with a carboxyl head group, and then we pyrolyze it to release the CO2 from that carbon, and the rest of the molecule sits down as a reduced phase. And you can measure that. This is picked up by, actually we both published similar methods at the exact same time. We're unaware of each other's work, and I'm now collaborating with the group in Japan on this, and they've really gone forward with it, and I'm going to show you some of their efforts in just a minute. This is an example of a measurement of an isotope inside a molecule, right? So we're no longer measuring the whole molecule, we're just measuring one specific position. In this particular case, it's the carboxyl. This is pretty cool, I think. And it actually has really ignited interest in a variety of different labs internationally, not this work per se, but this idea of getting at the specific site. We heard yesterday from Katie about isotopomers and of methane and other CO2 and other forms. And here's an example of methane with hydrogen and carbon-12. Here's one with carbon-13. Here's one with deuterium, and here's a clumped example with both deuterium and carbon-13 together. These are all sort of isotopologues of each other. That's a simple molecule. That's about as simple an organic molecule as you can get. But more complicated organic compounds also have isotopic ordering in them, or at least theoretically they should, and we'd really love to see that, right? And it conceivably carries in it biochemical information that could be really helpful and really tell stories about the origins of those molecules. So I mentioned this pyrolysis method. This is the work we did, and then Yoshida's lab in Japan, working with Alexis Gilbert, have really pushed this forward and continue to today, and I'll show you some of their work in a minute. And also, NMR can map the position of isotopes in a molecular structure. And if you have really strong NMR techniques, you can actually get it at per mil precision, right? So these guys in France, Richard Robbins and his team, are measuring not only hydrogen, they worked in hydrogen first, and they could do that pretty well early on, but today they're now doing carbon isotopes in specific positions in kind of a per mil, couple of per mil precision, which is amazing, right? Isn't that cool?
It's great, and then it kind of moves.
I'll take that off. How about that? Okay. Yeah, I think it's got covered. And then finally, there's been a lot of work in sort of high-resolution IRMS, particularly for the isotopomer and isotopolog work of the small gases. John Eiler at Caltech has been pushing forward a technique where we have an ion resonance mass spectrometer that kind of takes a molecule and breaks it into little chunks and then holds those ions and then sends them one at a time to the IRMS. And you can measure the isotopes in a high resolution fashion on the IRMS system. So this ion resonance mass spec is called an Orbitrap. That's a commercial name for it. And then the IRMS is, the kinds of instruments you've already been working with. So it's a mass spec technique, and the inlet to that can be a GC, for example. So you could send individual GC compounds in and then have the fragments be sent off and analyzed, and then you can, like a puzzle, put back together the positions of the isotope distributions. So these are all techniques that are now here today available for sort of looking and interrogating the intramolecular isotope ordering, and that's led to, for me at least, some confusion about terminology. So I want to highlight this very helpful figure from a review that John Eiler wrote a few years ago now. This is an organic structure, and he's pointed out onto it different kinds of isotopic ordering that we're interested in. What we're all familiar with is sort of a single substitution on a molecule of one or the other isotopes. Or you could have two isotopes together on the same molecule, but not necessarily sharing a bond. So they would be non-adjacent multiple substitutions. In this case, he's showing deuterium. Over here in this example, you have oxygen-18 and deuterium. They're both rare isotopes, and they share a bond. So that's the adjacent substitution, multiple substitution, what we know as clumping, right? That's the clumping term, but that's adjacent multiple substitution. And then you could have multiple substitutions or a position specific, so it could be in one place or the other, and the new techniques are allowing us to begin to map that out. So there's this terminology that we have to kind of get more comfortable with as we have really opened, or these folks have really opened a whole new frontier in molecular isotope measurements. And they're highly specialized labs at the moment, but I can envision that this would be something that is expanding in the field of research. And here's one of the examples that might show why people are interested in this. So this is Alexis Gilbert, who's really worked, he did his work initially in France with the NMR, and now he's in Tokyo, at Tokyo Institute of Technology, and working with the position-specific and the NMR techniques there. This is a study of glucose, and glucose has 6 carbons on it, and when you break it apart into 2 pyruvates, and then it can be broken ultimately to ethanol. And the lab in Nantes works a lot with food purification and verification applications, and so you can imagine that being French, they like their wine. You want to know if there's been, or other alcoholic beverages, if there's been sugar added to it that is not indigenous to the wine plant. Well, you can tell C3, C4 just by bulk isotopes of the glucose. That's pretty straightforward. But they were interested in sort of figuring out if like pineapple juice was also being adulterated. That's a CAM plant. And so they were able to show that position-specific patterns differ amongst the different forms of photosynthesis of the glucose, and that translates into these ethanol differences. Isn't that cool? And so there's a really elegant application. It's also a financially, motivated application, right? So to me, that's good news for us natural, science types, because now that means instruments might get, pushed forward in a useful and affordable way. Yeah.
So the way that they're breaking down glucose to pyruvate and then to ethanol again?
Yeah.
So this specific compound, the machine that they're using, they can take, it's like all front-end work you have to do to break down the compound.
So some of this is the pyrolysis approach, and so that's what he's worked on quite a bit. But you could also begin to now map some of these different. That's a 20 per mil difference within the structure for the CAM. This dashed line is the CAM. The glucose. And so you can begin, we're now at the NMR point where you can begin to get that precision adequate to pull that apart. Yeah, right? Right? Are you guys all feeling like Beaker and your hair's on fire, right? So, and then I just included in your handout is some of the text that sort of summarizes some of these findings, that the positions in now, this is confusing terminology, but we're talking about the atom position, C3 and C4, and the atom position of C2 have these different enrichments, and the sucrose from CAM can differ from the C3 and C4 plants. And they don't know why exactly, but they're kind of speculating about a biochemical pathway for that to happen.